Okay, time to do some calculus of the very tedious variety. I'm going to make a slope field here for number 2 at the 25 grid points from in the first quadrant. Looks like they want this time. So 1, 2, 3, 4. I want this grid. So those points on the axes and these ones here. Alrighty. Now, let's see. What's my differential equation? So y prime plus y equals 2. Y prime plus y equals 2, or in other words, dy dx, which is the same as that, is equal to 2 minus y. That's what we're talking about there. So this one is, I think the correct vocabulary is to say that it's homogeneous in x, which means that the x coordinate doesn't matter. So if I look at my different y values, everything's going to be the same. So when y equals 0, the slope is 2. It's my attempt at slopes of 2. When y equals 1, the slope is 1. When y is 2, the slope is 0. Then negative 1. And then negative 2. That one's a little wonky. Oh well. All good? So if you wanted to sketch solution, or just to visualize solution curves that go through this slope field, you pick the starting point. So it looks like this is an asymptote here. And whatever you pick as a starting point, if this is time, then you might not want to go backwards from there. But if it's just, some function, then need to do that. All right. Number 4. Solve the initial value problems in exercise 3 and use a graphing utility to confirm that the integral curves for these solutions are consistent with the sketches you obtained from the slope field. Let's see if I still have... Did I ask you to do... I thought I asked you to do number 3. Oh, because it was just in the book, right? We just kind of drew. Let's see. I remember that I drew that. Where is that piece of paper? Well, that may be gone forever. Oh, no. Nope. Here it is. This corner of this one right here. So those were our slope fields here. So we'll go ahead and solve them. This was the differential equation was dy dx is equal to 1 minus y. And let's go ahead and solve that. So separating my variables, the whole thing has to come over. This is a real classic separation of variables problem here for lots of reasons, because it has a lot of application, turns out. And yeah, I guess that's all I want to say about that. So what's the antiderivative of this? The thing that trips us up often is this negative sign. It is natural log 1 minus y, but because of that negative there, that pops out, and that makes a big difference. This is like the antiderivative of 1 is just x plus c, because that has to be moved over to this side before we exponentiate. So let's do that. Natural log of 1 minus y is equal to negative x plus, I'll call this c1 now because it just absorbed a negative sign and I don't want to give somebody the false impression that it's the same c. And then I can do the e to the, so that gives me 1 minus y is equal to e to the negative x, and then plus c1 up here, but that can come down as a new constant. I'll call that c2. and then I can solve for y. So y is equal to my constant C2. Actually, I want to write it this way. 1 minus C2 e to the negative x. Okay, and then I had 3 points. I had the point 0, negative 1. I had the point 0, 1. And I had the point 0, 2. And we'll go back and look at those sketches in a minute. So if I plug 0 in for x, then this just turns into all 3 of these. If I plug 0 in for x, this just turns into 1. So I get y equals 1 minus C2, y equals 1 minus C2, and y equals 1 minus C2. And those are the different c's. So in this one, C2 must be equal to 2. Here, C2 is 0, and here, C2 is negative 1. So that means the solution to the differential equation with this initial condition is y equals 1 minus 2 e to the negative x. Here it's y equals, this is a 0, so it's just y equals 1. That whole thing gets knocked out because the C2 is 0. And here y equals 1 minus 1 e to the negative x. I guess this is parts A, B, and C, if you like to keep track of that kind of thing. Probably a good idea. Excuse me. So, I was doing some matrix stuff there. Excuse me. Let's see what we need to do here. I want to make a, what we want to do, I guess they just want us to confirm that the graphs look like these sketches that we made. So I'm just going to go ahead and graph all 3 of them. So 1 minus 2 e to the negative x, and y equals 1, and y equals 1 minus e to the negative x. Now before I go hitting that graph button, I'm going to set a window. I'm going to look back at the book. There, negative 3 to 3 was their window there, so let's follow that. And then we'll graph. So we're expecting that it's going to look like this, right? Oops. Wow. What happened there? Something's wrong. I guess that's why we do this, right? To make sure. C's to negative. Oh. Oops. Let's see. So it looks like our sketches by hand turned out better than our calculator work. We made that mistake there. There we go. And that looks pretty. Looks like our sketch is pretty good, right? Cool. Want to see something really cool? I should have just done it on this one here. So let's go to y equals. Put those in again real quick. I wrote a slope field program for my calculator, and I'm trying to remember if I should do the slope field thing. I'm trying to remember how my slope field program works. Program my slope field. Isn't that a cute name for it? It wants that this is the asking for the derivative, our differential equation, and for us, what was it? It was 1 minus y. 1 minus y. Oh, and I need to set the window first. That's what I need to do. So, all right, so we're going to make it from -3 to 3. And we're going to also graph. I'm trying to remember if I want to put these in, put my functions in first or not. So what do I have? Y equals 1. I'll try it this way and see if it works. Y equals 1, y equals 1 minus 2 e to the negative x, and y equals 1 plus e to the negative x. Geez, that's not going to work, and this is also not going to work up here because that's the wrong kind of sign. There we go. Okay, so let's see if I go ahead and graph those. And then, let me try, I'll see if this is going to work. I'm actually going to go to, where is it, in Format, I think, and turn my axes off so I can see the slope field better. Okay, so now my axes are off. Did you know you could do that? And there's the 3 solutions. And now, let me try, see if this will work. My slope field, 1 minus y. It's going to draw those. Oh, what? Oh yeah, okay, it's working. It's not the greatest program ever, but it works pretty well. So there's the slope field. Pretty cool. All right. Again, if I ever see you in person and you want these, I think that these programs, which I wrote kind of a long time ago on a TI-83 Plus, I think that they transfer okay to a TI-84. So if you want them, or I can show you the code. They're not too complicated. If you're interested in that kind of thing. All right, groovy. All right, where does that put us now? What tedium do we have next? Number 8. Use a slope field in exercise 5 to make a conjecture about the effect of y sub 0 on the behavior of the solution of the initial value problem as x approaches infinity. That's what he drew in this book again. And check your conjecture by examining the solution of the initial value problem. Now, we can't actually do that second part because this is one that can only be solved using a different technique that we didn't cover in this unit or this section. So we're just going to do the first parts of that, which are to go ahead and look at the slope field. Let me bring it over here so you can see it. So looking at this slope field here, and we want to make a conjecture about y sub 0, in other words, the starting y value that will help us understand the what's happening with the limit as x approaches infinity. And just kind of by inspection here, not really thinking about what the solution is. I don't know if you can see this, but it looks like there's a line, a straight line that comes right through here, that if you happen to start on that line, then you're just going to continue on that line. right? Continue, continue, continue on that line. Do you see that? And everything, if you start above that line, it looks like as x approaches infinity, you're going to shoot up to positive infinity. And if you start below that line, then you're going to go off to negative infinity. So it's like a very sensitive. If you're close to that line, but just a tiny bit above it, you eventually are going to peel up, and likewise if you're below it. So what is the equation for that line? We could try to figure it out by inspection. It looks like it's got a slope of, I don't know, 1/2 maybe. And it looks like it goes across the axis at, oh, I don't know, maybe somewhere around 1/4 or something like that. So, what is my differential equation here? It's y prime is equal to 2y minus x. And if y prime, excuse me, if y prime is constant, in other words, if we're looking for, like, what is the slope of that, the solution where the slope is just constant. If y prime is some constant, in other words, if we're on a solution where the slope is not changing, then I think we see pretty quick here that we must be talking about a slope of 1/2. Right? Yeah, sure. So I think all we need to say here is that there's an asymptote with a slope equal to 1/2 if y sub 0 is above, then the limit as x approaches infinity of the y of the function is positive infinity, and if it's below, then the limit as x approaches infinity of the y values will be negative infinity. Yeah, it's good? Yeah. They say something just like that in the book. All right. How about number 14? Here we go. Euler's method. So again, on any kind of assessment, you're not going to have to do more than a 2-step Euler's method. So this is just annoying, I think. But let's see. Am I going to do, I think it's good practice. Oh boy, 16, I've got to do 10 steps. And 18, I guess there's just 2 of them. And then in 20 part A, I hope you didn't actually do the all of those. You guys, you just do the first one. I'll show you how I would do that, because I wrote a program to do Euler's method, which I think I showed you in the last video. All right, anyway, for number 14, I guess we better do this. I'll do 14 and 16. How about this? I'll make you a deal. I'll do 14 and 16 all the way, and then 20 I'm going to use my little my program that I wrote. So for 14, I have, where am I starting at? At the point 0, 1. My dy dx is x minus y squared, and then my delta y I get by multiplying dy dx by delta x, which is, what is my delta x here? I'm going from 0 to 2 with steps of a quarter. So 0.25 is my delta x. Okay, so if I'm going by steps of a quarter, then I need to get to here. That's my target. And all right, let's go. So x minus y squared is -1, and then that times just -0.25. So that's 0.75, and then x is going to get nasty real fast. So I got 0.25 minus 0.75 squared is -0.3125, and then I multiply that by a quarter, same as dividing by 4, -0.0781. I'll try keeping, well, I guess I'm going to do it. I'm going to write down 3, but I'm going to use that number. That's how I did it last time, isn't it? And then take that and add that to this. So plus 0.75. So that's 0.672. And then I'm going to take that number, that's my y. I'm going to do negative that thing squared plus the x value, which is 0.5. That's 0.049, and then I'm going to divide that by 4, and that's my delta y, and add it to 0.672. And then I'm going to do my x value, 0.75, minus the previous answer squared. That's 0.282. I'm going to divide that by 4. And then I'm going to add that to 0.684. Then I'm going to do my x value, minus that squared. That gives me my slope. I'm only going over a quarter of an x, right? So that's why we have to divide it by 4. So divide that by 4. Oh, did I forget to? Looks like I forgot to write one of them down. I think I'm okay here. And then add that to this. Boy, I'm crossing my fingers here that I didn't make a mistake. 862. And then I'm going to do my x value, 1.25, minus that answer squared. That's my slope. I mean, if computers hadn't been invented yet, well, I guess you wouldn't have this calculator, but this would be the motivation right here. And then divide that by 4. 0.127. And then my new x value. Oh, wait. Oh, no. I'm going to take this answer and add it to this. That's my new y value, 0.989. And then I'm going to take my 1.5 minus that answer squared. That's my new slope. And then I'm going to divide that by 4, because that's what you do when your step size is 0.25. And I'm going to add that back. I guess I'm going to write it down, 1.31, 1.31. Oh, this is totally different numbers that I wrote down than what I said. Not a good idea when you're doing Euler's method or any other time. So what is this? This is my delta y. So I need to add that to this. And then I'm going to do 1.75. This is finding my new slope minus, so I'm just talking, you know what it is, I'm just talking to myself here. The answer squared, that's my new slope, 0.497. And if I divide that by 4, that's my new delta y. And then if I add that to 1.120, I get 1.244. Okay, you don't have the book to look at. I do. So I'm going to look. Whatever it says, I'm just going to claim that my answer is right. Yep, my answer is right. Now, in all seriousness, that is actually the correct answer. They have the book, they reported only to 2 decimal places. They have 1.24. So that is good. Whew. Isn't that fun? Okay, this one's even better. It's got 10 steps. Great. And then this is the last one of these beastly ones that I'm going to ask you to do. Oh gosh, I'm going to have to give you free pizza for Euler's method. That's just depressing. Delta y is equal to dy dx times delta x, and the delta x here is 0.1, so I can just do a slide the decimal place over. I'm going to start at 0, 0, and we're going to get by tiny little steps. They seem tiny when you have to do it by hand. Okay, here we go. So, I am going to do e to the negative 0 is 1, and then that times 0.1 is 0.1, and that plus 0 is 0.1, and then e to the negative 0.1 is that, and then sliding the decimal over is just going to write down the same number of them there, and then that's my delta y, so I need to add that to the 0.1, and then I need to do e to the negative that, and then I need to slide that decimal place over. I know how to do that without the calculator, but I want to have that number in there to use, so just in case you think I'm being spectacularly lazy or something. I'm not. Then I'm going to add that to 0.190. And then I'm going to do e to the negative that. Then I'm going to move the decimal place over. Then I'm going to add that to 0.2 0.273. Then I'm going to do e to the negative that. How's that accounting career looking? Or actuarial work, that's another good one, if you like this sort of thing. Divided by 10. Not to poke fun at actuaries. Many of my best friends are actuaries. Hope I'm on track here. The old 420, 0.420 that is. And then I do e to the negative that. So these are creeping down, these slopes. And divide that by 10. Mercy, uncle, I give up. Then I add that to 0.420. And then I do e to the negative that. And then I divide that by 10. Oops. Like that. And then I add that to 0.486. Then I do e to the negative that. And I move the decimal place over. And I add that to 0.548. And I do e to the negative that. And I move the decimal place over. And I go buy a computer. And I add that to 0.606. And I do e to the negative of that. And I move the decimal over. And here we go. And I add that to 0.661. And there was much rejoicing. Whew! All right, let's see what the book says. Oh yeah, 0.71. Nice. 2 in a row. Okay. It's good. Number 18. Show that the solution of the initial value problem, y prime equals e to the negative x squared, is that. So what? So y prime equals e to the negative x squared with the initial condition 0, 0. They want to show that this is a solution, that y of x is equal to... How do you show that something is a solution of a differential equation? Well, you just like plug it in, but the thing you're plugging in is the actual function, right? So when you take the derivative of this, then according to fundamental theorem of calculus part, what we call part 1, then y prime is equal to, what happens when you take the derivative of an integral? It just cancels out the integral, and there's no funny business if it's just a number to x. The x just drops in. So it's just that, so y prime equals that, and that's all there is to do, right? So we have shown that. Use Euler's method with a step size of 0.05 to approximate the value from 0 to 1. This is 20 steps. Yeah, I think I really needed to clarify in this assignment. Maybe I will post something in Classroom right now that you do not need to do this by hand. I certainly am not going to. So if you wanted to approximate the area from 0 to 1, then that would be the same as doing Euler's method. So where's my calculator that has the Euler's method program? So Euler's method. So what's my dy dx here? It's e to the negative x squared. Right? Right. And my starting value is 0. And I want to go to 1. Oh, my change in x, sorry, my change in x is 0.05. And I want to approximate x equals 1. So it's thinking and doing it, and it gets 0.762. And that's the approximation for the area from 0 to 1, e to the negative t. So what's the point of this problem? The point of this problem is to show that using Euler's method, we just use that to approximate an integral. And if you think about, oh, well, why don't we just do the math and find the antiderivative? You can't actually find the antiderivative of this because it just doesn't work. So none of the methods that we have will lead to a solution or an antiderivative of that. So we can approximate instead using Euler's method, which is pretty cool. What's the significance of curves that are like this? This is another kind of point of this problem. This is a bell curve, and if you, that's obviously a very, very important curve in terms of distributions and probability and all that. This is not actually the equation of the bell curve, like capital T. The real one is, I believe it's 1 over the square root of 2 pi times e to the negative x squared over 2. I think that that's it. You can look that up if you want. But this is a version of, this is the one that is, basically these are like scaling factors, so that if you graph this one, then when you go over 1, that's 1 standard deviation. So if you found the area from like here to here, of course that's an integral now, right? I think maybe you do a little bit with this in Algebra 2, maybe. That the area here should be about 0.33 or something, or 32, which is the percent, right? That would be the percent of your normal distribution that would be between 0 and positive 1 standard deviation, and so on. So the area under curves of this type is like actually super important. All right, so blah, blah, blah. Enough about that. You could check this answer here. Is this the last part? And compare, yeah, compare with graphing utility. So let's get rid of this stuff here and just go in and graph e to the negative x squared. And let's look at that from negative 3 to 3 is probably fine. And then the y, it's not going to go negative, so how about 0 to, it's not going to go above 1 either, is it? So, oh, my axes are still turned off. Does that bother you? Oh, there it is. That is not the bell curve, it is a bell curve. And we just approximated the area from 0 to 1. So let's see what calculator does if I second calculate number 7, the integral from 0 to 1, and 0.747. That's interesting. So that's the exact area. Well, this is my Euler's method approximation, so that's a good example of how, like, taking all those little steps, even though we broke it down, that we got close, but this is still an approximation. So just for fun, if we went back and did my Euler's method program, what if we did like a bunch, like even smaller steps, like 0.01? Would that get us close to the 0.747 that the calculator is saying? So that'll be the end of me kicking this problem around, I promise. So program, we're going to do the Euler's method again, and dy dx is equal to e to the negative x squared, and I'm going to start at 0, 0. The change in x is, let's do 0.01, because it's a calculator. We don't care how much time it needs to take. That would be 100 steps. That would be fun to do by hand. Come on, little buddy, you can do it. Okay, so got a lot closer, 0.750, so most of the way there. And, okay, I know you want to see it, don't you? You want to see it done one more time with a tiny step size. It's going to take the calculator a long time to do this. Might just set it off to the side and let it think while we're talking about the next one. What do we do? Just 0.01? So how about 0.001? So that will be 1,000 steps. And we want to approximate x equals 1, and off you go. Okay, that's going to take a little bit. Number 20 is our last one. And all right, so I guess I'll do, well, let me set up the first one. So this is dy dx is equal to the square root of y over 2, and our initial starting point is 0, 1. So if you were going to do Euler's method by hand, just for the first one, x, y, 0, 1, dy dx is the square root of y over 2, and then multiply that by the delta x, which is here 0.2, so right. So you could go through, and the instructions are to find different approximations for that. We'll do that with the calculator in just a minute. It's still thinking about that last problem. And make a conjecture, and then the last part is find it exactly. So I'll go ahead and do that now while the calculator is busy. So to find it exactly, we just have to solve this. So separating variables, that gives me dy. This would go to the other side underneath, so that would be y to the negative 1/2 when I move it to the other side. I'm going to leave the 1/2 over here. That's usually the way we do that. Any constants, you leave them on the x side. And what's the antiderivative of y to the negative 1/2? Let's see. Bump the exponent up 1, and then divide by that exponent. And then that's 1/2 x plus c. So multiplying both sides by 1/2, I guess. So, or dividing by 2, however you want to think about that. And squaring both sides, so y is equal to that has to stay in there with that. That's not the same. You can't distribute an exponent, even if this is an unknown constant. Oh no! Look! Look at that. We killed the calculator. Okay, well, I guess you can't do that. So, yeah, there's the inside of my program. All right, well, I guess you can't do that. Might work on a TI-84 if you had that program on there. Might have enough memory. Okay, so here, with the initial condition 0, 1, then 1 is equal to 1/4 times 0, c1 squared. So c1 is equal to, I guess it could be plus or minus 1, couldn't it? So I think that we have y equals 1/4 x plus 1 squared, or maybe also this one. Maybe those are both solution curves that pass through that same point. Let's see. And they want us to make a conjecture about what's the value when x equals 1. Well, I'm not going to get the same thing. Interesting. Well, let's use this one and see what happens. So y equals 5/4 squared, which is that. Excuse me. So let's do Euler's method with, let's see, my dy dx is the square root of y over 2. Okay, starting at 0, 1, and my step size is 0.2, and I'm going to approximate x equals 1. So that gives me, with delta x equals 0.2, then I get a y value of 1.549. And if you don't know what that is, that's 1.5625. So you could try the other ones, and the other ones are going to get closer. But this video is way too long. I'm almost going to owe you 2 free pizzas. So there you go. This is, I think slope fields and Euler's method, they're really, really cool ways of using differential equations to visualize and approximate when we might not have another recourse. So definitely they're both very tedious, though, however useful they are, and better for machines than humans.